Thank you. As I said, I'm Niall O'Connor from GenoSpace, and today I'm going to tell you the story about how we built a secure and performant and developer-friendly encryption module that protects patient data, or the data of patients at the forefront of personalized medicine. And for us at GenoSpace, encryption is essential. We're governed by HIPAA, which is the Health Information Privacy Law. So encryption is essential. Performance is essential, especially when dealing with data at a genome scale, and performance is essential for patients as well when minutes really count. So I'll introduce the personalized medicine first and a bit about the company, and then we'll get into the project we did to really optimize our encryption module. And so what we're really doing at GenoSpace is building an operating system for personalized medicine. And personalized medicine means many things to many people. So if you're a patient, it means using the genetic information in your body to get better cancer therapies or find out different prognostic factors with your condition. If you're a doctor, it's about getting more precise diagnoses. And if you're a researcher or a drug developer, it's about finding new biomarkers or novel biomarkers in large collections of genomic data. So at GenoSpace, we've developed portals for all three of those segments. We have community portals where people regularly interact with one another, share data, share personal health information. We have clinical systems that are reporting on oncology patients on a daily basis, and we have thousands of researchers performing queries against petabytes of data. All this data is, as I said, protected health information, and so we've really focused on developing encryption modules that that are simple for developers to use and that also don't impact our ability to load data and retrieve data to answer important questions in healthcare. And so we encrypt a lot of data, and we do it in a variety of different ways. If you're sending us information, if you're sending us a file, maybe your transcript or your whole genome, we typically encrypt that using PGP encryption, and then that transits through our system. We process it and break it down, and we produce online records that are typically stored in AES-256-bit encryption, and that's where we're going to focus on tonight. It's the AES encryption that really impacts the delivery of results. And so we'll talk about the different aspects of the algorithm and what we've done to really make wise design choices about it. When we first started GenoSpace, there were a variety of different transparent encryption modules offered by like Oracle and Gazang. They were all very expensive. We had to layer on top of AWS different tools like these because AWS didn't natively support encryption of their EBS blocks or S3 object stores. The sales pitch that was given to us was that encryption is hard and encryption is costly in terms of performance. And because we were a small startup, we really couldn't bear the cost of using a lot of these tools, so we started to innovate ourselves. And so the first thing we did was just make it really easy for developers to encrypt things. So we used the Grails application development framework, and where we simply plug in our encryption module into our application framework, and a developer, all I has to do is just, I want to encrypt this generic data block. It's readable, it's understandable, and we can optimize the encryption routines without impacting the application as a whole. And so developers are largely blind to it, and those that are specialists in encryption technology can look at that themselves. So with some simple design choices when it comes to, as an application developer, when it comes to using encryption, you can have a really radical performance increase. So when we started out this research effort to determine what are the factors that impact encryption performance, we looked at different Java runtimes. We looked at key lengths, and we looked at cipher block operation modes and different algorithm configurations. And so we kind of broke them down, and tonight I'm going to just present a couple of the high-level ones that we found that were provided the most impact. The second part of this, I'm going to tell you how our application actually responded. Our population analytics portal responded once we implemented these changes. So I'll talk very briefly about the advanced encryption standard and just a little talk about the algorithm. So the algorithm is a block cipher, meaning that you take your large collection of data, and we used a 16 megabyte random file to go through some of these performance tests. And so that 16 megabyte file was broken down into 16 million byte blocks, and you then go through the different stages of the algorithm. So the first stage is key expansion. It uses the raw key that you provide, the actual 256-bit or 128-bit key that you provide, and it creates all the keys for the different rounds that you go through. In the first round, you just XOR the key with the byte itself. So you have a matrix of data, you just XOR that key with it. And then you go through these repetitive rounds, and depending on the length of your key, you'll either do it 10 times if you have 128, 12, or 14 times as your key length extends. And so in that iteration, what you're doing is you have your matrix and you're substituting bytes, you're shifting the rows, and you're mixing the columns. And it's just really like a Rubik's Cube on your matrix of data. And then you XOR it again with your round key. And so these are all the steps that are included in the algorithm. It's pretty simple when you break it down, but I'll show later on how Intel have actually improved on this, and this helps us with our performance characteristic as well. Because it's a block cipher, you also must consider the block cipher mode. And so you can go from simple but efficient block cipher mode to more complex and more secure. And what the block cipher mode basically does is it ensures that the same clear text doesn't result in the same ciphertext. And you can chain these blocks into more complex configurations, but obviously the more complex you make it, the less efficient it becomes. And so when we ran our tests, we found that ECB was the fastest by almost half as quick, or sorry, almost twice as fast as the longest block cipher mode of operation. But if you look then at what it produces, ECB isn't thought to be secure unless you're encrypting data less than 16 bytes, and that would be a pretty trivial amount of data. Basically, this is showing an example of how the block cipher is producing the same ciphertext for the same plain text, and you have information leakage in that scenario. So we chose to run the rest of our experiments or tests with the CBC cipher chaining block mode. It offers pretty good improvement over the worst case. It's got a 36% improvement with good security, and also some of the other block modes have different properties, like counter can be run, or it's more efficient for parallel execution. And so you really have to pick and choose your cipher block mode depending on what your actual use case is. We then went on to look at provider library. We were a Java shop, and it was a very natural choice for us to go and just pick Bouncy Castle. It's a native Java implementation. We didn't think much about performance in that regard. But just looking at provider library, you can see there is a 36% improvement on encryption time between NSS, which is a C++ implementation, and the default Java Sun JCE implementation of the crypto libraries. So provider library, just out of the gate, is an important choice along with cipher block mode. So then we encountered about 18 months ago, we encountered that Intel had made certain optimizations to their chipset from, I think, their Xeon family range onwards. And it happens that AWS support this out of the box as well. So all AWS instances from M3 onwards use a chipset from Intel that has this AES-NI optimization. And basically, they've, and we can see here, they've created new instructions to capture all the varieties, all the steps of each stage in the algorithm. So if we look at that full round, and previously we saw we have to iterate this full round, n times depending on the length of your key. They've boiled 4 steps down into one execution, and this matters. If we look at the provider library example that we saw previously, when we just compare provider library with AES enabled and AES-NI enabled, we see that the optimization provided by Intel provided a 93% improvement in encryption time over, and that's just literally enabling it and disabling it. You'll see the standard Sun JCE has a significant improvement, but not as much as that NSS C++ implementation. And then Bouncy Castle is doesn't have any sensitivity towards using AES or AES-NI, which was an important finding for us because we were using Bouncy Castle at the time. The next slide I think is important in the following one. When we started looking at key length, we have a lot of discussions with people, and a developer will often say, "Oh, I'll just encrypt it with a 128-bit key because it's good enough." But the standard allows you to use 192 and 256-bit keys. And we've shown that if you use AES-NI, there's very little difference in execution time of encryption routines when you use AES-NI. So what we saw here is a 20-fold reduction in their encryption time with doubling key length. And it's more obvious on this slide. So this is the one thing you take home. Basically, if you look at milliseconds gained by increasing your key length, so between 128 and 129, we see an 18 millisecond gain in encryption times. And then when you go from 256 to from 128 to 256, we see a 36 millisecond gain in encryption times with just standard AES and not using the Intel optimization. When we use AES-NI, our gain from 128 to 256 is less than 2 milliseconds. Again, we're doubling the key length, and we're having a 20-fold reduction in encryption time. This was a really important finding for us. So when we took these findings, and these were all just on kind of toy examples. We used 16 megabytes of random data, and we ran all these different executions through. So we wanted to find out, using the information we drew from the first phase, what would happen if we used it in our real-life population aggregation or population analytics platforms. And what these platforms are is we get hundreds and usually hundreds and thousands of patients. We aggregate all their data together, and you're able to ask questions like, show me the range of ages across these patients, or show me all the genetic mutations in these patients, and did they respond to a therapy? So these are complex queries. They're asking for lots of data depending on how many thousands of patients you have, and they're doing pretty big queries against large collections of data. And so we were expecting to see, using the optimizations that we've discovered here, we're expecting to see dramatic impacts in execution time when we're retrieving queries. And on average, we didn't really see that. We saw like a marginal difference in attribute request time, about 3.7%. But if we look at the blue line there, it's this one here. This is decryption time, and basically we saw a 46% reduction in decryption time. But in the end, it only resulted, and this is on average, but it only resulted in about 3.7% improvement in overall response times from the server. When we look at, so the one thing to keep in mind is that's over all attributes, and we deal with a lot of sparse attributes. So not every patient has an observation at a particular location. So not every patient has a mutation. And so If we look at something like platelet count for this study, it was a study of 754 patients. And we looked at platelet count, which was an observation that was available for every patient. So the block size here was about 28 KB of data. And the decryption time was reduced by 65%. And the response time was approaching about a 10% improvement in response time, about 8.9, which is significant when we're running large-scale analyses. So very often, if you're running a differential gene expression, you have to ask for all gene observations across all patients and do a massive comparison. And so when you make time improvements like this on a single request, you can see minutes difference in the responsiveness of your analyses, which run for 10 or 20 minutes. And in research, it's important to get answers back very quickly so you can test a lot of hypotheses. The one thing that we were very impressed with was when we started to scale forward and we started to have collections of patients in the hundreds of thousands, we started to see how AES-NI optimizations can really help. And so if you look at the baseline, it was 765 patients in our multiple myeloma research set. We went to 1,000 patients. We went to 10,000 patients. And we at 100,000 patients, we saw a 91% nominal impact in request time. And that was a 22 millisecond impact nominally. And what it showed to us was that the thing that starts to slow down is not encryption. The encryption routines are almost linearly scalable with data size. It's other aspects in your application like serialization and sorting and things like that that start to slow your application down as you hit into the 100,000s and millions. And so when someone comes up with an excuse like we're not going to encrypt it because it's going to be too slow, I think we have an ample amount of evidence that that's not the case, and we can keep pressing forward. So in conclusion, choose your provider library wisely. Not everyone has the luxury of not choosing Bouncy Castle. If you're distributing your Java application widely, then you probably will have to use a native Java implementation. Choose your cipher block mode very wisely because there are security concerns with which one you choose. Key length is not a factor. You should try to use the strongest encryption standard that the encryption length that the standard allows, because using some pretty basic tuning here, key length doubling does not affect the runtime performance. And in general, encryption is not an application bottleneck. Other factors are guaranteed to be holding back your application before encryption will be one of them. And it's scalable. It's a scalable solution. And so even as you press on into the millions of records, encryption should not be compromised at that point. So that's all I have. Does anyone have any questions? Sure. Uh-huh. Not on Neo4j, and we do encrypt the Mongo records individually. Yeah. So we basically on one partition of our MongoDB instances, it just looks like binary data that we just pump in, and the application then we have our indexes kept separate from it. Well, Bouncy Castle is, an open source group of people. They were probably a little late when Intel developed the AES-NI chipset. They were a little late to the game, but equally, it's a pure Java implementation. So getting down to that, instruction set code is going to be a challenge for a library like Bouncy Castle. It's probably a resourcing issue more than anything else, I think. It's important to know, though, I think. Any other questions? So all our patient records come from our customers. So we have a variety of different sources, clinical labs across the country, and yeah, those that we speak publicly about are the Multiple Myeloma Research Foundation. They're running a clinical study, and so we've thousands of patients from that alone. I don't think I would be allowed to tell what the most amount of, or the top line number for our patient records is, but you know, the example that we had there when we scaled up into the hundreds of thousands, we just started with our basic set and just scaled it, like just replicated it, and changed the patient labels and things like that. Any other questions? Thank you very much.